Yes, hello everyone. I'm Subhojoy, and this is something that is interesting. We are going to have this introductory sort of course on in topology, and which I'm sure a lot of you are interested in. And before we begin, I would probably like to sort of have everyone say their name and where they are, what year they are in, which college they are in, and maybe where they are, geographically, so that just to get to know all of you. Let me start with myself. I'm Subhojoy. I'm currently in Bangalore. I'm an assistant professor in IISc. And I work in geometry and topology, and this is something I do my research in. And I've taught topology many times in different countries, in fact. But this is the first time I'm doing it online. So, and it's not going to be a traditional, sort of course that is in a classroom because of all the difficulties of this video and so. So it is mostly a reading course. So you'll have to sort of read up on the topics that I'll be discussing, and I'm there to supplement it in some ways, and maybe some whet your appetite in some sense. Okay. So that's about me. So why don't we go one by one, and let me see. So yeah, and just tell me a little bit about your name and where you're from and what you're doing. Okay, yeah. So yeah, it's good to see a variety of people. A lot of you are probably going to take this course at some point formally. Those who are planning to be math majors, etc. But nevertheless, I'll try to sort of have somewhat of a light. As then the next few weekends we'll see, depending on what people are interested in, I'll try to focus on topics that interest you. So let me try to share my screen, where I'll sort of, it will serve as some kind of whiteboard. Let's try to do that. Okay. Right. Okay. So hope it's all visible now. So let me start. So I wasn't sure what this audience was going to be, so I've kept it, very light at the beginning, right? But hopefully it will be of interest to you. So let me start with some sort of very basic stuff. Okay, so sort of going back to the beginnings of topology. Okay, so this was a few hundred years ago. So so initially it might seem it's I'll be talking about something which is different from topology. So namely, I'll be talking about graphs, right? So suppose you take a graph. Okay, so and this for us is something which has vertices and edges, right? So there's some number of, let's say you have some collection of vertices, and then you have some edges between them. So that's what a graph is, right? So maybe it looks something like this. Maybe there are sort of two edges between vertices. We can allow that. Maybe there's some edge from a vertex to itself. We can allow that. So that's a graph. But then we also want it to be connected. Okay, so it's connected, and I suppose you can all guess what it means. So something which is not connected would be, so let me just. The not connected would be if you have, something like sort of this, right? So that's not a connected graph, but this one is, right? So this one, the one that I drew, is. If I delete, so maybe if I delete an edge which is here, so then it becomes disconnected, right? But but if we add this edge, then it's a connected graph. So that's what a connected graph is. And suppose it's also, I want something that is planar. Okay, so it's going to be, let me put it this way, write it this way. It's going to be also embedded in the plane. Okay, so, and by this I mean that no edges cross. Okay, so something which is not embedded is, well, if I look at the same kind of graph that I was looking at, so suppose I have this and that. Okay, so that's, the edges are crossing, so we don't want that. Okay, so this particular graph, you can embed it, right? So if you just, instead of making it cross, if you take one of these edges and go around the other way, then that's the same graph, so it connects the same, it has the same edges between vertices, etc. But now this time it is embedded. Okay, so suppose I start with such a sort of connected graph embedded in the plane. You take such a graph. So something that happens, so let me just write, take any such graph. Something that happens is this graph will divide the plane into regions, right? So here, these three edges here enclose a region R1, and then there's an R2, there's an R3, and the region outside, we say, is the fourth region, R4. Okay, so that's also counted. So the outside region is counted, and then so the theorem, this observation from a long time ago, is that if you count the number of edges, okay, so first count the number of vertices, then subtract the number of edges, and then you add the number of faces. Okay, so let me use orange here. That always equals 2. Okay, so no matter what connected graph embedded on the plane you take. Okay, and this is a theorem. Does someone know whose theorem it is? I mean, who first observed this? So by the way, you are welcome to stop me and ask questions, or just like in a classroom. Okay, so or you can also, I think, raise your hand. I don't know how that works here, but there's some kind of button you can click that raises your hand. Let me see if I can see that. Okay, so I'm not sure whether, okay, yeah. So can someone tell me, whose theorem it is? Yeah, I can't hear you, but yeah. Yes, that's right. I think I can lip read, but somehow I wasn't audible. I'm not sure why. So let's see. Maybe I have to unmute you or something. In any case, I think so a lot of you would know this. So this was by this is Euler. This formula is called Euler's formula. I mean, Euler had several formulas. So let me just make sure I can see you folks.
Just a quick suggestion. If you have something to say, you could also put it in chat. This is for the audience.
Yeah, okay? That's right. Yeah, you can do that. Okay, so so this was approved by Euler, 1707 to 1783. I looked up Wikipedia. All right, and this is kind of it's a nice thing to tell non-mathematical people. Okay, so if you try it, with someone who's maybe a kid, or someone else who's not into mathematics, you say that, okay, draw a graph and you put vertices and put edges and you count them, and it's always turns out to be. So for example, here, let's actually, so we haven't tried it with this guy. So here the number of vertices is what? So let's call it V to be short. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 is the number of edges. Number of edges is let's see, it's 1, 2, 3, 4, 5, 6, 7, 8, right? So you have, oops, there's the wrong color. So that's 8, and the number of faces is well, so these are the number of regions rather. So I'm calling it regions. I'll talk about why I said faces a little bit later. So number of regions R is equal to 4. I've already numbered them, right? And then so you see that 6 minus 8 plus 4 is equal to 2, right? So so let me go over the proof very quickly, right? So this is something that there are a variety of proofs of this, okay? By the way, this was also, Euler was also credited not only with this beginning of topology. I'll say how this is related to topology, but this is also, he's also credited with beginning graph theory, okay? And this sort of kind of the beginnings of the subject. And so this is kind of a basic theorem. There are plenty of proofs, and some of them are quite elegant. I'll give you some books to look at the very end. But there's a standard sort of the first instinct proof, which is this theorem, is to go by induction, right? So let me first do a special case though. So let me, so I'll talk about the proof by induction, but there's a special case that one starts off with, okay? So the special case is the following. So the special case is when so when there is only one region, so the connected graph determines defines only one region, which is outside, right? And so what's an example of something like that? So well, if you have some bunch of vertices, so you have a graph like this. Okay, so suppose you have maybe this, maybe that. So that's an example of a graph. There's only one region, right? So this outside region, this R1, let's call it R1, right? So by the way, can someone tell me what such graphs are called? And I guess this is a basic question. Some of you are already in your second or third years. I think none of you are audible for some reason. Can you unmute yourself? Is that?
Is it something related to roads? Because Euler solved that bridge problem.
Yeah, that's right. That's another famous sort of problem that Euler solved. That's right. That's true. But this I'm talking about is a kind of a class of connected graphs.
The trees?
Yes, that's right. It is exactly. That's exactly right. So these are called trees, right? So this is a tree, right? Because I mean, I've drawn it suggestively. It sort of has that kind of branching feature. And there's one feature of a tree. So a tree is some graph which has no cycle, right? So cycle is. So let me draw a cycle in the original. Let me highlight it, and maybe in yellow if it is visible. So this is a cycle, okay, right? And that's a cycle, and so on, right? So these are cycles are sort of closed loops, made up of edges, right? So a tree doesn't have any cycles. That's another way of defining what a tree is, okay? And for a tree, it's kind of easy for you to sort of check that the number of vertices, let me draw it in, because the number of vertices minus the number of edges, okay, is always equal to 1. Okay, so what happens when you try to sort of make a tree bigger, for example? You have to add, so you would take an existing vertex and you have to put in an edge and you put in a vertex, right? So that's what you do. So whenever you put in an increase an edge, you have to put in a vertex, right? So I mean, I'll leave it to you to, sort of see how number of vertices minus number of edges of a tree is always equal to 1. So this means that this sort of Euler's formula holds, right? So holds is always true for a tree. Holds for a tree. So this is the Euler's formula that maybe I'll kind of box it to something. Okay. All right. So this is so it's true for trees. So how do we do it in general? So this sort of in general, as I said, it's a sort of the proof by induction. Okay. So in general, you sort of prove by induction on, let's say, the number of edges. Okay, you can do it, with number of vertices and the number of faces, perhaps. So you can, there are a variety of ways you can prove this. So I'll do it by number of edges. Okay, and how does the proof go? Well, so the base case for your induction is when the number of edges is 0. Okay, so when that happens, then the graph, what's the graph? So the graph, it has to be a connected graph, right, with 0 edges. So then it's just a single vertex, okay? And so Euler's formula trivially holds, right? So the Euler's formula just gives you 1 minus 0, so 1 vertex, 0 edges, and 1 region, which is the sort of the outside, right here. That's the region, and that's 2. Okay, so the base case is satisfied, and then there's the inductive hypothesis. So assume that Euler's formula holds for a connected graph with, let's say, capital N edges. Okay, and so that's your inductive hypothesis. So let's prove it for n plus 1, right? So then if you take a connected graph with n plus 1 edges, okay, so if it is a tree, then there's nothing to do, right? You're done, because you already noticed that, it's always true for a tree. So then we are done. If not, so what does that mean? That means that somewhere in the graph there is a cycle, right? Maybe let me draw a bigger cycle. Maybe there's a sort of a bunch of edges, okay, sort of all connected up and closing up, right? And there is a lot, the rest of the graph is doing something which I'm not drawing. So that's the cycle. I was drawing it in yellow, right? So it's marking. So that's a cycle. So what you do is, so there is a cycle, there's some cycle. There could be plenty of cycles where you take an edge belonging to a cycle and delete it. Okay, so let me write, so delete an edge belonging to some cycle. Okay, so any edge in the cycle. So in this case, maybe let's take this edge, right? And you can, so you delete it, right? So what happens when you delete this edge? Okay, so let's observe a few things. So first of all, so when you delete, so let me just write it like this. So then what happens is, number one, the number of edges decreases by 1, right? So you want to apply the inductive hypothesis after all. So let me write it in green. So the number of edges decreases by 1. You've deleted an edge. Okay, so the second thing that happens is, so the second thing to notice is that the graph, the new graph, is still connected. Why is that? Well, it's because you took some edge from a cycle, right? So now if there is a cycle, right, and so then if you delete an edge of a cycle, well, you might worry that now you've disconnected it because you can't now go from this vertex to that vertex along that edge that you've deleted. But since it's a cycle, you can go the other way around, right? So you can go the other way around, and it's easy to check that now. So this new thing is still connected. Okay, so these are two observations. The third thing that you observe is that what happens to the number of regions. So earlier, when you had that cycle, let me draw it again. Right, so you have the cycle, you have that edge inside there that you deleted. You had a region that the cycle enclosed, right? You had this region, let's call it R1. And there was a region which was maybe on the other side of that edge that you deleted, right? So let's call that edge, that edge orange like we were doing. But when you delete that, right? So then when you delete this edge, then R1 and R2 merge, right? And become one region. So the number of regions, let's denoted by orange, the number of regions decreases by 1. Okay, all right. So now what happens? Well, so 1 and 2. So let me. So say if you look at 1 and 2, 1 and 2 means that in the new graph, the inductive hypothesis holds, right? So the Euler's formula is true because you get a connected graph with n edges. So you know that Euler's formula is true for the new graph. And if you look at 1 and 3, right? So this tells you that if Euler's formula is true for the new graph, it's also true for the original graph, right? Because to get from the new graph to the original graph, the number of vertices remains the same. Number of edges goes up by 1 and regions goes up by 1. So if you look at V minus E plus R, then that remains the same. So then this implies that Euler's formula is true for the original graph. Okay, so this is a sort of a simple enough theorem. So this completes the induction, right? So this is a simple enough proof, right? So you just sort of this is one of those proofs where you follow your nose. Okay, so you have an idea that, okay, maybe it can be done by induction, and then you just follow your nose, you'll come up with this proof. There are nice proofs without induction, okay? So I'll give you references. So there are sort of very elegant proofs using a little bit more graph theory. But let me talk about one corollary. Okay, it's one consequence of this theorem in graph theory, which is which is very useful. Okay, so it might seem that, okay, why is this useful? So this fact about Euler's formula, but it is used all over the place. And one of the consequences is to show that K5 is not a planar graph. So I'll explain what K5 is. So the K5 is a graph where you have 5 vertices. Right? It's a complete graph, the 5 vertices and all edges between them. Okay, so all possible edges you have to take. Okay, so when you try to draw it, you'll find that you'll be crossing edges. Okay, so this corollary says that there's no way, it wasn't just my drawing. There's in fact no way that you can embed it in the plane. Okay, it cannot be. There's no planar, sort of realization of this K5 graph. Okay, so how does one use Euler's formula to prove this? Well, suppose it was planar. Okay, so last time we did proof by induction. Okay, so this is another technique of proofs that I guess you are all familiar with. If you suppose not, right? Suppose it is planar. Suppose K5 is planar. By the way, if you try to draw it, I mean, maybe, you know, you said that, you know, why didn't you try to draw it without crossing? So let's try to do that. If you take these guys, so far it's embedded. Okay, so then I cross this way. So instead, if I go around, okay, right, so that's fine. Oh, by the way, I missed one edge here, right? So there was another edge here. So far, so this can be connected to this can be connected to that, right? So far it's embedded, but since it's a complete graph, you have to, you know, join all possible pairs of vertices, right? So there's no way to now connect this to that, okay? And this is what the corollary says, okay? So there's, you know, no matter how clever you try to be, you can't sort of connect up. All right, so without crossing an edge, right? So how does the proof work using Euler's formula? So if you look at the number of vertices, so that's 5. What are the number of edges? Someone quickly. Can someone say what the number of edges are? Yes, okay, somebody did it in the chat. It's 10. It's because it's 5C2, right? So you're joining all possible pairs. So therefore, Euler's formula will tell you that the number of regions, okay, I was using orange for that, the number of regions, it has to be 7, right? Okay, if there was a planar embedding of K5, has to be 7. But why is this? So we want to get a contradiction, right? So how does that work? So you notice that each region must have more than or at least 3 edges around it. Okay, so the way that complete graph works, you don't have regions that look like this, right? There are no double edges between a pair of vertices, right? Each pair of vertices is a single edge, right? So there's no, so this doesn't happen. So this doesn't happen, and neither does a single edge around the vertex like this. So this also doesn't happen, right? So there's at least, if there is a region, it must have, so these two don't happen, but you must have at least 3 edges, right? So this is sort of the, should have at least 3, okay? But so now if you try to count the number of edges this way, so what happens if you add up? So let me write it here. So if you add up the number of edges around each region, you get, can someone say what you get? So it's do you get all the edges, or do you get the number of edges, or what do you get? Can someone unmute themselves, perhaps? Anyone? So if I say get the number of edges, so that's wrong, but can you correct it? Yeah, that's right. You get twice the number of edges. That's right. Why? Because if you take a region, right, then an edge that's surrounding it, one of the edges that's around this region, that's in the border of the region, that edge also belongs to a neighboring regions, right? So when you add up all the number of edges, you're counting that edge twice, right? So okay, so you have these 2 observations. Each region must have at least 3 edges, and then if you add up these, you get twice the number of edges. So that means that twice. So this time 1 and 2 imply that if you look at twice, let me use the color I was using, twice the number of edges, that's greater than equal to 3 times the number of regions, right? So 3 times the number of regions. Okay. So now when you apply it to, so that must be true, right? So if this is planar, this must be true. But then we already computed the number of edges and number of regions. So that was 10 and 7. So if you plug those in, so this would imply that twice 10 is greater than 3 times 7, which is definitely not true. That's the contradiction. Okay, so that's the proof that K5 is not a planar graph. Okay, it's a consequence of, once you know Euler's formula, you can deduce various facts like these, and there are plenty of proofs in graph theory that very nicely use Euler's formula. Okay, so now you might be thinking that, okay, so this is all graph theory. I signed up for a course on topology, right? Where's my, where's topology? Where's the shapes? Where the topology is about, sort of it's the study of shapes in a broad sense, right? So where's the shape? Well, so it turns out that you can think of all this that we were talking about as happening on a sphere, right? So a planar graph, the planar graph is, or it can be thought of as, can be embedded, let me write this, can be embedded on, or let me say, in a sphere. So the basic topological space. Somebody mentioned balloons. So this is something that topologists will call a sphere, right? Oops, let me try to draw it again. So I'm also getting used to it. I can do it better on a blackboard, I suppose. Okay, sort of blackboard is easier to go sort of one round with a chalk. Okay, so that's my sphere, and you can think of the graphs we were drawing on a plane earlier. You can just imagine them, sort of lying on this sphere as well. Embedded on the sphere, again, embedded means no edges cross. And this time you can see that, so the region, the outside region that we were counting, so we had this, maybe this R1, R2, etc. Let's see, in this case, you just have 3 regions. This outside region is enclosed, is indeed enclosed by, these set of edges right here. So that sort of this graph defines that region on the sphere and so on. So so secretly, what I was talking about earlier, there's about planar graphs and something about actually about graphs on a sphere, and what in the Euler's theorem can be thought of as saying. So this is another way of sort of saying. So we say that the Euler number of a sphere is 2, okay? Because if you draw an embedded graph on the sphere, which breaks it up into these regions or these pieces, which are nice, then if you count the number of vertices minus edges plus number of regions, you get 2, right? And the thing where topology starts really is the observation that, let me write it like in, maybe I'll write it in orange, that the Euler's formula, if it's, so Euler's formula is true for any surface that looks like a sphere, that is topologically equivalent. Okay, and this is what one of the notions that we'll have to kind of learn, or you learn as we go along in this course. So topologically, let me draw it, and let me write it in red. This is going to be one of these important notions that you'll be learning. Equivalent to a sphere. Okay. What does that mean? Well, if you deform your sphere, so let me sort of informally say what topological equivalent means. So you can think of topologically equivalent means that you get a surface where you deform your sphere into that surface. So you're allowed to deform by stretching or bending. So stretch and bend, but not tear your surface. You can't make a hole, right? So you can tear or even glue up. Okay, you kind of you identify points. Okay, so that you're not allowed to do. So for example, this particular sphere, so what you could do is you could, maybe you can stretch it somewhere, okay? So maybe you kind of, you sort of deform it, you stretch it, so now it's no longer a round sphere, but topologically it will still be a sphere, right? It's still something that you get by deforming. So maybe if you can deform, you know, stretching these vertices with them, maybe. So sort of vertices and edges, you kind of stretch it so that they kind of, so you can imagine this is made up of, you know, some stretchable material perhaps, or something like that, okay? So, or maybe it's some kind of, you know, sort of a rubber thing. Okay, so, right, so whenever you do this deformation, it's still an embedded graph. You're not changing the number of vertices, number of edges, number of regions. Okay, so it is still going to be the Euler number on this topological sphere is still going to be the same, right? It's still going to be 2. Now you can ask, okay, so what happens for a different surface? Let's see what happens for a surface that looks like this. Okay, so oops. So by the way, what is the surface called? It looks like a tire tube or donut or vada or something. Yes, that's right. So somebody said, so for a torus. Okay, so what happens on a torus? So let's try to draw a graph, an embedded graph of the kind that we were wanting on a torus. So the way that we are going to do it is we are going to, oops, this was, so the color for an edge was green. So let me start with this curve, embedded curve here. Let me put 3 vertices here. You can put any number, right? And now let me put these edges in. Okay, that goes around like that. And these are, so if I put these 2 in, then this bounds this region, right? So this region is something that you can sort of flatten out to be something that, you know, sort of looks like something on the plane that's bounded by sides all around. Okay, so this certainly it's just like a rectangle, right? When you sort of flatten it out. Okay, so that's a valid region, and you can do the same. You can add another edge here, maybe, and then you get this region here, and then there is another region that kind of goes around and sort of wraps and sort of into the whole. So you get these 3 regions, and everybody sees 3 regions, right? So in other words, what happens to the number of vertices? The number of vertices is 3 in this case. Number of edges. Okay, so let's count the number of edges carefully. So we had this. We added these 3 guys, but then in between these red guys, there are 1, 2, 3 edges, right? So there's a total of 6 edges that we that you see in this picture. Okay, and the number of regions, as I said, is 3. Number of regions is 3. So it turns out, and this is a fact, we might get to it later on, is that the Euler number of a torus is 0. Okay, so no matter what graph you embed on a torus, so I should say a little bit more about region being. So region, you necessarily need to be able to flatten out. So for example, if you just draw maybe a triangle or something, okay, so on the torus like this, well, the inside region is definitely a valid region. So this is a valid region, right? So that is something you can see that you can flatten it out on the plane. But so the complement is not a valid region. Okay, so this has some kind of funny, this hole in it, which you're not really sure about whether it's, something or not, so this is not a valid region. So you want the regions to be sort of pieces that are just in a planar case. They're sort of actual regions that you can sort of flatten out on the plane, right? So it's sort of, sort of just like before. Okay, so so whenever you have that, by any graph that breaks up your torus into valid regions, you do the Euler number formula, and you always get 0. And not just for any torus. The point is that you can do it for any. Let me use another color. So any surface or any surface topologically equivalent to a torus, right? So topologically a torus. Okay, so let me sort of quickly show you an example of something which is topologically equivalent to a torus. This one. Okay, so can everyone see this animation? Yeah, so everyone is familiar with this fact, I suppose, that for a topologist, a coffee cup and a donut are the same, and well, this animation is kind of useful. Right? So let's go back to, oops, where was I? Okay, so here, right, so where were we? So you had something which is topologically equivalent. Okay, so I think so we lost something, it's probably crashed or something. Let me sort of write it again. So anything topologically equivalent. So any surface, let me say any surface. So this Euler number turns out to be a topological invariant, right? So it's topologically equivalent. It classifies surfaces. Okay, this is one of the things that when one learns algebraic topology. Okay, so this is in fact so in topology, when you learn it, there are sort of a couple of different parts to it. Oops. So my screen is no longer shared, it seems. Could you share it again? It says that host disabled attendees. Can I be a host, maybe? No, I can't be a host unless. Let me try to share. Okay, I think now we are back. Okay, so right. Sorry about that. Some temporary glitch, it seems. Okay, so By the way, a coffee cup for a mathematician is actually a sphere with a handle. Okay, so let me. So a coffee cup is to a topologist. You will say that a coffee cup is it's a mathematical way of putting it, is a sphere with a handle, and the way that a topologist will draw it is, this is a sphere, and there's a mathematical notion of what a handle is. It's a circle cross an interval, so which gives you in this case, it will give you some kind of cylinder, right? And when you attach it, that chap is homeomorphic, or topologically equivalent, right, to a torus. Okay, so this notation here, this twiddle equal to, just means the topologically equivalent. Another nice way to visualize a torus is so another depiction, or another way to visualize something which is topologically equivalent to a torus, is a square with opposite sides glued. Okay, once again, these can be made very precise, and you'll be doing it, so when you read more about what quotient spaces are, you'll understand what I mean, that this guy, you take a square, and if you glue this side to that, and you glue this side to that, and by glue I mean that, so you are identifying. So if you are an ant and you kind of walk out this way, you'll come in that way, right? Because these 2 points are just opposite points, this side and that are the same, right? After identification, right? And so when you do that, you get a torus. The same for the top and bottom, right? So this is one way to see it, right? So when you glue one pair of opposite sides, you get a cylinder, and then you glue the other pair, then you get a torus, right? So this is one way to visualize it. So you start with the square, and then gluing this pair of sides gives you a cylinder, gluing the other pair gives you a torus, right? So this is a very standard construction, but this is going to be very useful for us all the time. Okay, so all right, so okay, so this is a torus, and so let me try to draw that graph we had before. So this guy, okay, so in this picture, okay, so we can do that. So here we can let me erase this ant. He's no longer needed. Okay, so this guy, this edge I've drawn is actually a closed circle, right? Because the top point and the bottom point are the same after identification, right? And then we had 3 vertices on this closed circle, and then we had added these edges, which again are, sort of connect up, right? These are actually, each of these are one edge. So I've got added these 3 more edges, and then the regions that we had marked. So this region, so this left part was going back to this, and so this is one region, and this is another, and then this here, the top part here is actually the same point as here. So in fact, if you think of these green lines as walls, you'll find that these 4 regions in these corners actually are sort of one connected region, right? So this is one way of visualizing. It's easier to visualize this, or at least once sort of, I find it easier to visualize than trying to visualize what happens in this 3-dimension and so on, right? So here you are working with a flat piece of paper, and it's easier to visualize. So exercise. So on a torus, so this is maybe an easy exercise. You can embed K5. Can embed K5 in a torus. All right. By the way, I'll send out these. I'll give these sort of set of exercises or things to think about, and maybe next time we'll kind of have a look at what people have thought about and about these, whether they've solved them, and if you have questions or sort of trouble, you can always let me know. But these are sort of things that you can do to make this course so that you can learn more from the course. A slightly more difficult exercise would be you can also embed a K6, a complete graph 6 in a torus. Okay, and then you can see how far you can go. Okay, can you embed K7 in a torus? Okay, what about K8? Okay, so number of edges grows very rapidly, so I wouldn't recommend you kind of actually but you can, so if you have a free afternoon or something and you're stuck at home, as we all are now, you can try to sort of play around and see what you can do. And so this is something that one can, this is one exercise that you can sort of amuse yourself with. Let me also, so the final thing I want to mention is that sometimes, so the thing is that, so the way it will work, I'll give some references at the end. So you'll read up some of these notions like, topological equivalent, what it means, and so on. What are surfaces, for instance, things like that, and then I'll try to supplement it with sort of more examples and so some kind of questions of interest, perhaps, exercises which are fun to do, things like that. But I guess the onus is on you to kind of sort of read and sort of learn. Let me sort of mention, before I give you the references, let me mention one last thing, is that, sometimes Euler's theorem, if you look up, on maybe on the internet, Google or something, the Euler's theorem is called Euler's polyhedral theorem or polyhedron theorem. Okay, polyhedron theorem, or Euler's theorem for polyhedra, and this polyhedron, oops, it's an N here, right? So what's a polyhedron? Well, you are all familiar with some of these, right? So there's a tetrahedron. You can have a cube. Various other shapes are possible. So let me sort of give you another glimpse of. So these are all possible. So these are different polyhedra. So all of these are topologically a sphere. Okay. So I'm going to. So Euler's polyhedral theorem is about things which are topologically. Oops, it crashes every time. I need to fix this. So Euler's theorem is always about. So oops, we've lost those, but it's something that is topologically a sphere. Okay, so I'm going to say it's actually a convex. Sometimes they're called convex polyhedra, or let me just say topologically a sphere. And let me draw a cube again. It's probably the easiest to draw. Slightly more difficult would be something like a dodecahedron or icosahedron. So the point is that in Euler's polyhedron theorem says the number of vertices minus number of edges plus the number of faces is always equal to 2. So this time, I mean, these regions are these flat polygons, right? So these regions are in fact sort of polygonal, right? These are the faces of this solid object, right? So so this is the same as what we sort of talked about for planar graphs, because the edges of a polyhedron form a planar graph, right? So note that, why is it the same as what we were talking about? The edge graph edge graph of a polyhedron is planar, right? And one way to see is that if you think of this this polyhedron that I've drawn here as a wire frame, and then if you just lower some light bulb, right, on it, then if you look at the shadow of this wire frame, right, so you'll get a planar graph on the plane, right, and that's exactly sort of capturing how the sort of edges and vertices of the edge graph are connected, right? So you can flatten, if you have this topologically a polyhedron which is topologically a sphere, so let's say it's convex, right? So then when you flatten it out by like a shadow, this is called a stereographic projection, right? You might have already seen it. So this you get a planar graph, okay? So here's another exercise. You come up. The exercise is you'll give an example of a planar graph. So come up with a planar graph that is not an edge graph of a polyhedron which is a sphere, right? A polyhedron, let's say it's a convex polyhedron, okay? And let me tell you about, if you drop the requirement that a polyhedron is convex or topologically a sphere, there are such objects, okay? So let me once again crash this. I want to show you another. Let me see if I can do it without crashing. It was working fine before. So this is an example, right? It's topologically a torus, right? But it's an object built out of these faces, which are polygons, right? Euclidean polygons. So you glue it, but it's topologically a torus. Okay. Oops. Right. It crashed again. Okay. So so here's an unsolved problem, right? In mathematics, we often have these. So the unsolved problem is what graphs, this is something actually in graph theory, I would say. So what graphs are edge graphs of let's say, let me call it non-convex polyhedron. Let's say something which is topologically equivalent to a torus, for instance. I think even that is probably not solved. Okay, so any case, yeah. So I just wanted to say that Euler's theorem is often, sort of talked about in connection with polyhedra and not just planar graphs, and all these things are intimately related. So as far as references, I mean, for this set of online things, which I recommend that you try to read as much as possible from, well, actually any source, but there's one sort of book that I would recommend is Basic Topology by John Armstrong. Okay, but I can understand it might be difficult to get hold of this book, so because now the libraries are shut, etc. But actually, any source which talks about any basic, sort of, source you find on the internet will talk about many of these things, and can refer to these. And for the next time, it would be nice if you kind of look up what this notion of topological equivalence could be, and we'll talk more about that next time. And I'll send out some questionnaire, I mean, just to gauge what people already know and what they would like to learn. Some of you are maybe a bit too advanced for an introductory course, but nevertheless, topology is something fun, and so one can actually teach it to anybody, and sort of high school students as well, and so on. And so it's always nice to hear about elementary things as well. Okay, so with that, I think we are done for today. We'll stay in touch. If you have questions, let me know, and we'll stay in touch. Oh, sorry, it's you're right. It's I think somebody's pointed out it's not John Armstrong, it's N.A. Armstrong. That's right. Okay, sorry. Yeah, John Armstrong is somebody I knew. Okay, so that's one Armstrong I personally knew, and it just, whenever I see Armstrong, I probably think of John. So yeah, so it's by some Armstrong who's not J. Armstrong. So yeah, but the book is called Basic Topology. So if you search Basic Topology and Armstrong, you'll find the book. Okay, so thanks. So any other questions or comments?
Excuse me, sir.
Yes.
Sir, I had a question. You had talked about phases and regions. So what is the difference between them?
So no difference. Yeah. So when I was talking about planar graphs, I was calling them, regions, because we like to think of, see, I mean, the whole kind of story of mathematics starts with us being creatures living on a sphere, which is Earth, right? And so you kind of mark out, sort of pieces of the sphere, you enclose them by a fence and something, and you call it some, sort of land you want to cultivate. So that's a region, right? I mean, and whereas when you think of a polyhedron, I'm thinking of some shape that is sort of bounded by all these flat polygonal sides, and those we usually in English we refer to as faces of a polyhedron. Like, if you're of a diamond or something, then you have these flat faces as flat sides. So, but so you can go back and forth. Right? If you take a shadow of this polyhedron on the plane, these faces will correspond to regions, okay, and on the plane. So it's just something in English. For mathematically, there's no difference between the two, right? So sort of the faces and regions are really the same. Yeah, good question. Anybody else?
So once again, I have one more question.
Yes.
So the question is that when we were talking about torus, we talked about some three regions. We had those 3 points, yeah?
Right.
So
let me go to these. I'll go to the picture. Right. Okay.
A bit earlier. Yeah. Over here, the outermost region, I'll call that the region which is in the hole. I mean.
Right. Which it kind of goes in and wraps around and comes out this side also, right? So if you kind of view it, so it's sort of difficult to see it's one region, right? But maybe a better place to sort of see that is this diagram, right? So if you think about, let me sort of use some other color. Perhaps I'd use blue here. So if you think about this guy, this joins up with this, right? So let me sort of draw these separately. This was the top, and now sort of when I go here, right? So then it connects with that. So then I have another one of these, but this side also connects with this side. So then you continue here as well, right? And then with this side connects with this side, and then so you get another copies. And each of these is sort of now you're kind of bounded by these green chaps. So you kind of, if you look at these 4 corner regions, they actually join up to form this bigger blue region, okay? And that's what you see in this diagram. You can imagine that to be the third region that goes somehow into the hole and comes out on this side. Does that answer your question? Is that what you were asking about?
No, sir. What I was asking was that in the left-hand side picture, we have one triangle-shaped region and another region which you said was not a valid region.
That's right.
Yeah. So is this one a valid region, the one we were talking about?
Yeah, that is a valid region, because you see that here I was able to flatten it out, right? So this region, so you can probably see it here as well. So all of these regions, the reason I chose, 3 things, you can imagine them to be to be sort of closely spaced. So each of these are thin rectangles, right, going around the torus. Okay, so a rectangle like this, you can always, so when you cut along the edges bounding this region, you can open out, and then it becomes a long thin rectangle that you can sort of embed on the plane. Okay, so the region, a valid region, is something which you can embed as an embedded region on the plane, which doesn't have any holes or anything like that, right? So it's like one of those regions that is bounded by a planar graph. And so so as you go along this curve and you look at these pieces that have broken this curve into, bounded by these red vertices, each of these pieces has this long thin rectangle around it. Okay, and so even if you go inside that, so I didn't draw many of these, but I could have drawn many vertices, then maybe it's easier to sort of believe this. So as you have many vertices, each of these have these tiny intervals, and then you have this long thin band around it. And each of these bands, it's easy to see that it's like a rectangle wrapping around the torus. You can, if you cut along the edges and you can open it out, it will become a flat rectangle, and you can embed it. Okay, so so this is sort of some exercise in visual imagination. So topology is, even when one does research in it, okay, so as one goes along, there's a lot of visual imagination that is needed, and is sort of one kind of employs, and so it's a fun subject that way as well.
Sir?
Yeah.
Over here in the torus, when we edges, we connected one point with itself, like the red point.
Right, that's right.
The green
that's true.
line. So when are we allowed to do that, and when are we not?
No, we are always allowed to do that, actually. Yeah. So so in our sometimes in graph theory you don't allow sort of edges to loop around it to itself and so on. So but in our case, the only thing that we need to worry about when drawing these graphs and trying to apply Euler's formula to a torus is that each region needs to be planar. It needs to be what is topologically called simply connected. Okay, so it needs to be something without holes in it, right? So it needs to be one of these planar regions, defined by a planar graph. But that's the only thing. So your edges are allowed to go and loop back on itself. You could have added more vertices and edges. So for instance, I could have taken, so in this picture, I could have taken these multiple curves like this, right? And then each of these intersections, I put a vertex, right? So now you have many things. And now maybe it's easier to see that all of these regions are, valid regions, because every time you see these 4 vertices here, so they bound some, some rectangle, which is definitely a valid region. Okay, but now you've added more edges and more vertices, so it's sort of harder to count. That's why I just took 3. But if you now, even for this guy, if you count the number of regions, you get these rectangular regions, and number of vertices, number of edges, apply Euler's formula, you get 0, right? Which is the Euler number for vectors. Okay, so yeah.
Okay, we have another question.
Yes.
Sujay in the comment section.
Yeah, if I draw a point on a Mobius strip and draw a line along the mid-axis, yeah, that's is the region divided into regions? Yes. So we'll do these experiments maybe next time. That's a good question. The Mobius strip is one of the favorite spaces that people sort of learn about, right, when one is starting out in topology. And this is some experiment one can actually do physically with a pair of scissors and some glue and a piece of paper. So maybe actually, so next time I'll ask, I'll send out some message on Telegram or by email saying that so you come with some piece of paper, and so we can actually do it and sort of you cut along with scissors in the center and see whether you get something which is disconnected, and then we'll do or you talk about some related experiments as well. So the Mobius strip is coming. So I mean, yeah. So don't. Yeah. So it's definitely going to come to topology, right? Whenever everyone is discussing topology, the Mobius strip is going to come. So don't be disappointed if I didn't mention it in the first lecture. You can't go without Mobius strips and Klein bottles, and there are various other topological spaces. Okay, great. Yeah. Any other question? Okay, well, so yeah, sorry. Someone was.
I guess, they could always continue to ask questions on the Telegram group, and maybe you could.
Yeah, sure. So I'll send out a questionnaire also to gauge, what people would want to hear about, etc., and how when the sort of feedback for this this particular sort of session. So please feel free to let me know your comments and things you would like to see also. Okay. Right. Okay. Someone says I'm unable to join the Telegram group. I guess these are issues would be sorted out by StemNet, and you all be able to participate. Right. Okay.
Yes. Thank you. And I would like to say that. Just a second, please. 1 second. I'll just. Yeah, thank you, everybody. And thank you, Professor Subhojoy, for this very interesting and colorful and very kind of visually imaginative lecture that you did. It was, I hope it's inspiring to everybody as it was for me. And we will see you. We look forward to see you again in the next session next Saturday, and to look forward to all the resources and exercises that you would give us for the next week. Yeah.
Sure,
thank you.
sure. So thanks, and see you all next Saturday. And in the meanwhile, we'll be in touch.
Yeah, and I'd like to say this to everybody else. Could you please fill out a feedback form that I'll share right here. It is also shared in the Telegram group. So if you can't join the Telegram group, I shall add you. Right. So please fill this form out. So that we get feedback on how to improve things, and that will really help us. Okay. Yeah, and I posted this link also in the Telegram group, so please don't forget to fill this form. Thanks.